All right, we're continuing our discussion now of kinetics, which is reaction rates or the speeds in which chemical reactions happen. Last time we were discussing generally how we could track these rates or look at them in differential form, change over time. This study will look at how we can use that differential form to then look at speeds of a reaction or amounts of concentrations at particular points in time. So far we've looked at concentration change over time. A lot of times though we want to look at a reaction and say, hey, 10 minutes into this, where am I going to be? Or just at some generic point in time, how much of this stuff's going to be left? And so to do that we have to take our differential forms and translate them into integrated forms. We can do this with the use of calculus, and so we're going to convert that rate of change, or change in concentration over change in time, to a linear expression. For a first order reaction, this will be some reaction that's dependent only on the concentration of a single thing, and there'll be a direct relationship to it. Mathematically, this says that the rate is equal to the rate constant times the concentration of some participant in the reactant. When we look at this for disappearance, we can say that the rate of disappearance of A, or negative dA dt, equals K times the concentration of A. We know this already. We've written these for first order reactions already. We're going to translate this and rearrange to gather like terms so that we have negative dA over A equals K dt. Now we're going to integrate this. Those of you who haven't had calculus can just take our word for it. Those of you who have can verify. If I take the integral from time equals 0 to time equals t of dA over A, and also take the integral of K dt from 0 to t, we'll see that on the left side we get the natural log of A evaluated from 0 to t, comes out to natural log of A at time t, equals the natural log of A at time 0 minus kt, or y equals mx plus b. This fits the form of a line. So we're not saying it's actually y, we're saying it fits that form where my y would be my natural log at some time, my intercept is the natural log at the beginning time, and my slope then is negative k. So it's all dependent on t. When we do this, a very useful thing comes out of the equation. If we want to go back and see how long it takes for half of my original concentration to disappear, we can do this with a little mathematics being applied to the previous reaction, and we call this value half-life, and it's very important. We look at it when we're looking at decay reactions or other things of that nature, because for first order reactions this is going to be a constant value. So most radioactive decay follows this. There are a few other reactions that follow this. You'll often see this reported when they talk about the lifetime of pharmaceuticals in the body. They often report them as half-life, so this is an important concept. So what we're saying then is that the half-life at the time to 1/2, obviously if it's half the concentration is going to be gone, then half is left. So at time t we're at 1/2 of my original, and so we can sub this into the equation and get ln AT over A naught equals negative KT 1/2, and we know that AT over A naught is 1/2 or 0.5. So the natural log of 0.5 equals negative KT 1/2, or the half-life T 1/2 equals 0.693 over the rate constant. Applying this to a reaction, we'll take a look at the following question. The decomposition of a certain insecticide in water follows first order kinetics with a rate constant of 1.45 per year at 12 degrees Celsius. Some quantity of this insecticide is washed into a lake on June the 1st, and the concentration is measured to be 5 times 10 to the minus 7th grams per cubic centimeter of water. Assume that the average temperature of the lake remains 12 degrees Celsius. What will the concentration of the insecticide be on June 1st of the following year? So here we want to say, hey, we've spilled this insecticide, oopsie daisy, 1 year out, how much of it will still be there? Something that's useful for us to know is that we can write our half-life equation or our first order kinetic equation in log form, which we've done already, or we can convert that into exponential form and have AT equals A naught e to the negative KT. So we're going to apply the exponential form just because it's easier to isolate the concentration of T in that manner. So I'm going to plug in the values that I know. I know my initial, my A0, is 5 times 10 to the minus 7th, and I know that the half-life is 1.45 per year, and I want to go over a period of 1 year. And so if I allow that to happen 1 year later, we're still at 1.2 times 10 to the minus 7 grams per cubic centimeter. So there's still pesticide around. The next part of the question wants to know how long will it take until we decrease to 3 times 10 to the minus 7 grams per cubic centimeter. I don't know, maybe they're interested in this because this is a safe level for fishing or a safe level for swimming, whatever, but we can tell them that. We rearrange our equation to solve for t as shown below. We're using the natural log form, and so natural log of AT over A naught times negative 1 over K equals t, sub in the appropriate values. Natural log of 3/5 times 1 over the rate constant tells me it takes about 0.35 years for this to happen. So until we get to that threshold, it's not very long. The half-life then of this process can be calculated from our previous equation. T1/2 equals 0.693 over K, or 0.693 over 1.45 for a year. It tells me it takes about 0.48 years for half of the original concentration to disappear, or roughly half a year. And then finally, how long until we reach 1/4 of its original concentration? Maybe this is the point where we're not worried about it at all anymore. If that's the case, we go back to our equation that we used in part B, and instead of putting in 3 times 10 to the minus 7 over 5 times 10 to the minus 7th, we just know it's going to be 0.25. The ratio of those two things will be 0.25, so we put in natural log of 0.25 times negative 1 over 1.45 per year, and that lets me know that I need to go almost a year. And that would make sense, as the 1.2 times 10 to the minus 7 that I saw for 1 year is just shy of 25% of my original value. We can carry this a bit further to a second order reaction and apply the same logic. In this case, we're usually depending only on the concentration of one reaction or one reactant in the reaction, but it's typically squared. Now this can be two different things that are being required to collide with each other to make a second order reaction, but that makes the kinetics much more difficult. So we're going to assume that it's one thing that has to collide with itself. And so my rate would be Ka squared. Or if we follow our similar tack that we did for first order and phrase this for disappearance, it says that negative dA dt equals K times the concentration of A squared. We can rearrange that again, get negative dA over A squared equals K dt, and apply some calculus just like we did before, and we'll see that that then is a power relationship, and so we end up with 1 over A at time t equals 1 over A at time 0 plus KT. This also fits the form of a line, only this time instead of being related to natural log, it's related to inverse. So same type of line, different value that it's linear with. So here we go with a second order reaction problem. It says the following data were obtained for the gas phase decomp of nitrogen dioxide at 300 degrees Celsius. So I'm going to convert NO2 to NO and 1/2 oxygen gas. My times are given here. I've probed the reaction at 0, 50 seconds, 100 seconds, 200 seconds, and 300 seconds. And I'm watching NO2, which started at 0.01 moles per liter, disintegrate down over time. I've also gone ahead and taken the two orders of reaction that I know. First order, I've taken the natural log of all the concentrations at those times, and then I've taken the inverse, or 1 divided by those concentrations at those times, and tabulated them, because this is the easiest way to determine the order of a reaction, which is typically in AP chemistry what they want us to do with a second order reaction, or a set of data, determine its order. So the easiest way to do this is to plot the two and see which one is linear, because we saw from the two reactions or equations that we generated from our calculus for the integrated rate forms that they have to be linear. First order is linear with natural log, second order is linear with inverse. So here's the graphs. If I take the natural log and graph it versus time, it makes a plot that at first glance appears to be somewhat linear, but if you look at it really closely, there's also a bit of a curve to it. So we'll put this in the maybe column until we graph the inverse. Oh, look at the inverse. The inverse is almost perfectly linear, while the natural log form is slightly curved. So we can put a big nope next to the natural log. That's not quite linear, so we will ignore that. It's not first order, therefore this reaction appears to be second order. And that is what we do. We can also find the half-life of a second order reaction or reactions beyond in much the same way. If I go back to my integrated form of a second order rate law and let A at time t equal 1/2 of A at time 0, just like we did for first order, and call t half-life, t1 half. I can do the substitution, work it down with some algebra, work a little further, and see that my half-life is 1 over k times the original concentration. The problem here is that the half-life depends on concentration, so it's not constant. Assume that we take a reaction with 1 mole per liter and we work it down to 1/2. We let it disintegrate to 1/2 the original concentration. That means that at that point, when I go to evaluate the next half-life, my starting concentration is no longer 1. It's only 1/2. And since that shows up in the half-life, it's going to take longer then to reach 1/2 of that value or shorter, depending on what we're doing. But it's definitely dependent. It's not going to be constant. So beyond second order, things are going to get complicated. But that's not a big deal for us because that's not something we typically deal with a lot in AP chemistry. So you should have seen here how we take differential rate laws, convert them to integrated rate laws, and use them to determine information about reactions at certain points in time. Not just their rates of change, but their actual concentrations throughout the reaction. And coming up, we'll talk about the collision model and how the collision model relates to all these different interactions within the reaction and can help us to start to determine the pathway or the mechanism for the reaction.